Annenberg Media.
Most of it's luck, but the skill is about 10%. If you know the 10%, normally you'll win.
You have to quit while you're ahead because that's the only way you'll beat the game.
In Atlantic City, the name of the game is gambling. Millions of visitors flock here to enjoy the excitement of the casinos, where games based on random behavior provide opportunity for gamblers to hit the jackpot or lose their shirts. For the casino, though, it's never a gamble. In fact, it's a successful business.
In casino gaming, the house edge is very small, unlike the lottery, where it's like 50%. We have a percentage advantage in most games that is less than 1%. But by attracting thousands and thousands of people a day, in fact, some days we think we get as many as 50,000 people walking into an Atlantic City casino. That small edge starts to eat in, and we start to generate revenues which average in an Atlantic City casino about $700,000 per casino per day.
So to ensure profits, casinos don't need to deal marked cards or use loaded dice. All they need to do is keep the gamblers gambling.
We're looking to attract, retain, and return customers to Resorts International. We'll attract them through newspaper ads, entertainment specials, drawings on the floor.
Once at the tables, gamblers actually have a very real chance of winning in the short run. The random nature of the games ensures that the outcome of each individual bet is unpredictable. But in the long run, the casino's slight edge provides them with consistent profits.
When a player first comes in, his chance of beating us is about 50-50. When he's ahead, he can walk away. We have no way to bring him back to the table. Most players, though, enjoy the fun of casino gambling, and they want to stay at the table for a longer period of time to enjoy that, and that basically gives us a bigger edge.
So as another day ends, the casinos count their winnings, and the gamblers lick their wounds.
I broke out about even. It was fun.
How'd you do?
Lost my shirt.
You what?
Lost my shirt.
You gonna come back?
Sure. Come back all the time. Lose my shirt every week.
I won a little bit. About $50.
That's a lot.
Oh, no, it's not. I'll be back next week.
Yeah?
Maybe next week I'll do a little better. This is my 44th trip.
It may seem counterintuitive that a business based on random behavior can make big bucks. After all, the word random conjures up the image of such wild, completely unpredictable behavior. Well, that's not the whole picture. Take the most common randomizing device, the coin toss. Well, I can't predict whether it's going to be a head or a tail, but that doesn't mean it's entirely unpredictable. See, I do know all the possible outcomes. I'll either get a head or a tail. And if I flip the coin for a while, I know that about half the time I should expect heads and half the time tails. It's the same principle at work in the casinos. They can't predict the individual outcome of a specific bet, but they can find a long-term pattern. It's this order that can be described with the mathematics of probability, the subject of our program. We'll learn the language of probability, including the terms experiment, sample space, and event. We'll learn how to calculate the probability of an event. We'll see how we can apply our knowledge of combinations to help make these calculations. And finally, we'll see how the logic of probability can make some amazing coincidences seem downright ordinary. We're going to look at some random events and study them through probability. We'll first need to devise an experiment. Nothing fancy, just a set of rules to govern our study. The rules allow us to repeat the experiment in the same way for as many times as we need to. An experiment can be as simple as flipping a coin 100 times and recording the outcome, or as fun as letting me loose in the casino to record my luck at the craps table. Whatever the experiment, we'll need to keep track of the results. We'll first need to determine what results are even possible. We call the collection of all possible outcomes for a given experiment the sample space, or S. For a single coin toss, it's a head and a tail. If we toss a coin twice, the sample space will be 2 heads, a head then a tail then a head, and finally 2 tails. With the possible outcomes defined by the sample space, we'll want to focus in on particular outcomes. We call this an event. For instance, we can ask about the event a head and a tail in 2 tosses. 2 different members of the sample space produce this event. Another event is getting at least 1 tail. In that case, the event consists of these 3 members of the sample space. We've just learned the first steps in constructing a probability model. Set up an experiment, figure out the possible outcomes, that's the sample space, and define particular outcomes we're interested in. Those are the events. The final step is to figure out a probability for each event. One way to do this is to repeat the experiment thousands of times. Then we can actually see what happens in the long run. This requires a lot of patience and a lot of time. It helps if you haven't got anything better to do. Just the situation mathematician John Kerrick found himself in as a prisoner of war during World War II. His experiment was to flip a coin 10,000 times. The sample space, a head and a tail, and the event he was interested in was getting a head. Here are some typical results. The first toss is a head, so that's 1 head for 1 toss for a frequency of 100% or 1. The next toss is a tail, so that's 1 head out of 2 tosses for a frequency of 0.5. The next outcome is a head, so that's 2 out of 3 or 0.67. As more and more tosses are made, the frequency of heads to tosses gets closer and closer to 0.5 or 50%. Based on the long run, we can say that the probability P of getting a head on a single toss is 0.5. Now, look at this. Okay, it's a trick coin, so we'll always get a head. That's a probability of 1 or 100%. And the chance of tails? Here, it's not even in our sample space. The probability is 0. These are the extremes of possible probabilities. In fact, we define the probability of an event to always be between 0 and 1. A coin like this is fun to have around, but to learn more about probability, we need to focus on something with a little bit of randomness. Let's try this. For a single roll of a die, the sample space consists of the numbers 1 through 6. To figure out the probability of specific events, we could do an experiment. Roll the die, say, 10,000 times. But with algebra, there's an easier way. If the die is evenly balanced, then each of the 6 outcomes is equally likely. So each number can occur 1 way out of 6 for a probability of 1/6. What's the probability of getting an odd number? 3 out of the 6 possible outcomes produce the event, so the probability is 3 out of 6 or 1/2. And what's the probability that we'll get a 6 or a 1? That can happen 2 ways, so it's 2 over 6 for 1/3. Get the picture? The probability of an event E is the number of favorable outcomes, that is, the number of outcomes that can produce the event, divided by the total number of possible outcomes. And what's the probability that we'll get a number from 1 to 6? Well, it's just 6 over 6, or 1. That makes sense, since one of the outcomes has to occur. In fact, it's a rule of probability that the total of all the individual probabilities in the sample space must equal 1. We now have the basics of probability. We can go ahead and use these skills to see how the casinos rake in the dough. We'll begin with my favorite game, roulette. A typical roulette wheel has 38 slots, 18 red and 18 black, and these 2 green slots, 0 and 00. When the ball is spun, it's equally likely to land in any of the slots. If you bet on the color red and it lands on a red slot, you win the amount you bet. If the ball lands in any other slot, a black slot or a green one, you lose. So the probability of winning is the total number of favorable outcomes, that's the 18 red slots, divided by the total number of possible outcomes, the 38 slots. That's about 0.474. What about the probability of not winning? In English, we call that losing, but in the language of probability, we call the chance of an event not happening the complement. Here, that's 20, 18 black plus the 2 green, divided by 38 for a probability of 0.526. There's another way to figure out the probability of the complement. On every bet, you must either win or lose, so that probability is 1. The probability of the complement, then, must be 1 minus the probability of the event. By comparing the probability of the event and its complement, it's clear the house has an edge built right into the wheel. You have a higher probability of losing than of winning. But that doesn't necessarily mean it's a bad bet. Maybe the lower probability is offset by a higher payout. So what we want to know then is how much money we can expect to make in the long run. That's called the expected value. Here's how it's calculated. Say that I make 100 $1 bets. Since the probability of winning is 0.474, then in the long run, I should win 47.4% of the time for a total of a bit more than $47. On the other hand, I lose the other 52.6% of the time. So that's a loss of more than $52. Well, as you can see, my losses outweigh my winnings by about $5. That's profit for the casino. So on average, they keep about $5 of my money for every 100 bet. That's a nickel for every dollar. You can try other ways of betting, like picking any one of the 38 numbers. The probability of winning is lower, but the payout is higher. Here, a dollar bet brings you $35. But here again, the house keeps about a nickel. In fact, if you look at any of the casino games, you'll find that the house wins roughly anywhere from a nickel to 15 cents on each dollar. And from my personal experience, the slot machines tend to have the worst payoff. And if you think your chances at the casinos are bad, forget about the lotteries. Almost every state now has not just one, but many lotteries. They generate much-needed income for the state, but for the player, they're not a good bet. To see why, let's go ahead and calculate the probability for a typical game.
Once again, the winning megabucks numbers for Saturday, April 6th are...
We'll need to return to our knowledge of combinations.
30, 33.
Probability of winning is the number of favorable outcomes divided by the number of possible outcomes. Let's first figure out the number of possible outcomes. In a typical game like Massachusetts Megabucks, players choose 6 numbers in any order out of 42. There are numerous possibilities. The exact number can be found with the combination formula. Okay, we have 42 elements taken 6 at a time, and doing the calculation gives us this many possibilities. Well, we don't need any complicated math to figure out the number of favorable events. Only one combination wins the jackpot. We've now found the probability of winning. It's pretty small. In fact, you have a higher probability of being struck by lightning than winning the jackpot. But remember, a slim chance doesn't in itself make the lotteries a bad bet. I mean, you don't expect the jackpot to be easily won. What makes it such a miserable bet is that given the very low odds, the jackpots are actually pretty small. Or, in probability language, the expected value stinks. Instead of making 5 cents on a dollar like a casino, in a typical lottery, the state keeps a whopping 40 cents on every dollar ticket sold. So, while it's easy to be swayed by million-dollar jackpots, it's a better bet to go to the casinos, and the best bet of all, put your money in a savings account. Of course, you may think that you can beat the lottery odds. You feel lucky, you have an instinct, or maybe you have a system. Certain numbers haven't appeared in a while, so they must be due. It's like if you flip a fair coin and get 5 heads in a row, the next one's got to be a tail, right? Well, it goes against our common sense, but random number generators, coins, dice, roulette wheels, don't work this way. They have no memory. You flip a coin, and no matter what's happened before, you have the same probability of getting ahead. So the outcome of one event is independent of another. Here's a string of heads and tails, and here's another. Well, one of these 2 strings I made up in the hopes of making it appear random, but since I made it up, it's probably not random. The other string is random. I had my assistant use a coin to generate it. Well, the big question is, which one is which? Many guess this is the random sequence. There are an equal number of heads and tails, and there are no long runs of either just heads or tails. But sorry, It's also the string I made up. See, it's actually too regular, because each outcome should be independent. In the short run of a random sequence, each head isn't usually balanced by a tail. Instead, this is the true random sequence, complete with a long run of tails and the variability associated with independence. It's this variability that actually makes gambling exciting. It means that even though the casino wins in the long run, in the short run, there can be big winners and big losers. You need to walk a fine line with independence and keep hold of common sense. If I flip a coin and get a string of, say, 30 heads, if it's a fair coin, it may be sheer luck. Or maybe it's not a fair coin. Maybe the probability of getting ahead isn't 0.5, but say 0.8. The point is, though, the flips are still independent. Just the probability has changed. And common sense also tells us that many events aren't independent. Everybody knows that if it's a clear sky at night, there's a good chance it's going to be sunny the next day. So the outcome of the preceding event does affect the outcome of the next event. So they're not independent. When making decisions, it's important to know whether we're looking at independent events. And sometimes independence can be tough to recognize and even tougher to believe. Take it from a basketball fan.
Once you get a streak going, it just seems like you can hit a shot with your eyes closed.
It's a great feeling, and when everything is going right, you know, there's no feeling like it.
When you experience success, that, you know, it breeds more success, and you know, you make a couple shots or spectacular plays, and you just feel it coming, and you just feel that, hey, there's no way I can miss tonight.
Players believe that you make several shots, you feel confident, you become relaxed, you get in a groove, and almost any shot you're going to put up is going to go in. Players describe it as the basket seems huge.
Tom Gilovich wanted to find out if this belief is true. Is a player really more likely to make a basket after he just made one? So he looked at the distribution of hits and misses from a season of Philadelphia 76ers games. His results are startling.
Whether you make a shot or not is influenced by a great many things. One thing, surprisingly, that it's not influenced by is what happened on the last shot. The outcome of the second shot is independent of the first shot.
So over a season, a star hits 55% of his shots, a second stringer only 40%. But for every player, hitting any particular shot is independent of the shot he just took.
If a player makes 2, 3, 4 shots in a row, that looks like the player is hot. What the fan doesn't understand is that even if we flipped coins, fairly often we'd get 4, 5 heads in a row just by chance.
Probability sure can be surprising, but I'm going to show an example that takes the surprise away. I had just hit town after a weekend of fly fishing. Never been here before. Good music. Nice shops. And then all of a sudden...
Steve? Steve Braun.
Sol Garfunkel. Is that you? My God, I haven't seen you in years.
Oh, God, it's 10, 12 years already.
At least, not since you flunked that math test, I think. I didn't recognize you.
Imagine that, running into an old friend. The probability must be tiny, right?
Well, the probability of seeing a particular friend is small, but the probability of seeing any friend is much higher. Believe it or not, I'm a pretty popular guy. I've got tons of old acquaintances, long-lost relatives, and countless former students. And in the course of a trip, I actually see a lot of people at the airport, in the shops, on the street. So there are a lot of chances to pass someone that I might know. We tend to forget about all these encounters. Let me show you another way to think about this coincidence, and maybe it won't seem so amazing after all.
Here we go again.
Excuse me, do you know me?
Must be a big world.
Excuse me, do you know me?
No.
Sure.
You don't look terribly familiar, why?
That's okay. No, it's all right. Must be a big world. Excuse me, do you know me?
No.
You sure?
Yeah, sure.
It must be a really big world. I know you. You're Steve Braun.
My God, it's Sol Garfunkel. How you doing? It's a small world.
Well, not so small, but it's really good to see you, too.
Good to see you. God, I don't think I've seen you for 10 years since you last flunked that math test, I think it was.
Probability helped me to see that running into an old friend wasn't so unlikely. And that got me thinking about another coincidence, finding two people in a group who share the same birthday. I decided to see for myself how likely it was. I first tried to find someone with the same birthday as me. I waited for a while, but nobody fessed up. It must be a pretty small probability.
You know, maybe I'm asking the wrong question. You get surprised not just when you find someone with your birthday, but when you find any two people who share a birthday. So let's open the field up to all possible birthday combinations.
Free cake if you tell me your birthday.
Hello, July 23rd.
Since there are so many more possibilities, the probability is much higher.
November 3rd.
As a matter of fact, it didn't take me very long to hit pay dirt.
November 3rd.
Hey, that's my birthday, too.
Bingo!
We can actually figure out the probability of finding at least two people with the same birthday. It turns out that the simplest way to do this is to first find the complement. What's the probability of finding no two people with the same birthday? We'll begin with one person. How about me? My birthday can be on any one of the 365 days of the year. And since there's nobody else in the picture, my probability of not having the same birthday as someone else is certain. It's 1, or 365 over 365. Okay, so I stop the first person I see. In order not to have the same birthday as me, hers must be on any one of the other 364 days. The probability of that is 364 divided by 365. So what's the probability that the two of us have different birthdays? It's just this times this. For this solution, we've turned to a rule of probability. For independent events, the probability of one event and another event both occurring is the product of the probabilities. Here, that's 0.99. So it's pretty likely we don't have the same birthday. But let's continue our walk down the street. I'll ask the next person I see. His birthday needs to be on one of the 363 open days left. That's a probability of 363 over 365. And again, we multiply. If we work our way up to 23 people, the probability of no two people having the same birthday works out to be about 0.5. To find the complement, we subtract from 1. That means the probability of at least two people out of 23 having the same birthday is an incredible 1/2. And if we ask 50 people, the probability increases to 0.97. It's almost certain.
There are two important lessons to be drawn from the birthday problem. First, it's sometimes easier to find the probability of an event by first finding its complement. Second, when you hear about something happening that seems to buck impossible odds, make sure you're looking at it correctly. We tend to personalize events. We ask, what are the chances that a particularly rare outcome happens to me? The answer is usually pretty small. But if we open up the whole field, what are the chances that a rare outcome happens to someone in a group of people? The probability can be pretty high. That may explain some of the things that you read in the tabloids. It's not going to explain this one. Computer talks with the dead. But it may explain why you read about someone winning the lottery twice or someone having a dream about the future that comes true. I mean, come on. Everybody in the world dreams, and everybody dreams about the future. Sheer volume, whether it's millions of people dreaming or millions playing the lottery, means that almost any outcome that can occur will occur. And unfortunately, that can include some tragic events.
We tend to think the chance of getting in a car accident is small, especially when we're in the driver's seat. For a single trip or a short time in the car, that's true. The only problem is that over the course of a lifetime, we spend a lot of time in the car, and that adds up. Each year, automobile accidents kill almost 50,000 people. We can use probability to figure out what the actual risk is of getting in a fatal accident. We'll first figure out the yearly risk. A rough estimate is the proportion of fatalities in a year to the number of people who spend a significant amount of time in a car. With 50,000 deaths and about 150 million frequent drivers and passengers, the probability of dying in an accident is 1 over 3,000 per year. That's pretty high, and it gets worse. Most of us plan on using cars for the rest of our lives, and no matter how good a driver you are, the more you drive, the more likely you'll make a mistake or become the victim of someone else's mistake. The risk then accumulates with time, or in familiar algebraic terms, risk is a function of time.
For 1 year, the risk of a fatal accident is 1 over 3,000. But since the probability accumulates with time, the risk goes up 1 over 3,000 per year. So after 60 years, the probability is up to 60 divided by 3,000. That's a 1 in 50 chance of dying in a car accident in a lifetime.
This is just a rough estimate, but it's sobering. If you're sitting in a class of 50 people, chances are one person in the class will die in a car accident. With odds like these, we need to take every precaution we can. Drive carefully, wear a seatbelt, and don't drink and drive, because you're gambling with your life. Driving brings us back to the basics of probability. We have no way to foresee the behavior of individual drivers, but by studying long-term patterns, we can make accurate predictions about the future. And in this case, the predictions tell us we need to improve auto safety. To figure out how we can make driving safer, we'll need to look at the big picture. But this problem is so big, we'll want to focus in on what's really important. The skills to help us do that are the basics of algebra that we've developed in this series.
A good start is to look for underlying relationships behind traffic fatalities. For example, maybe there's a function between driving speed and the number of deaths. To see if that's the case, we might try drawing a graph. And if we find a function, we'll want to put it in the concise form of an equation. This will allow us to make predictions, like how many lives we can save for every mile we decrease the speed limit. And as we build our model, we'll probably need the help of some of the techniques that we've developed, like factoring or solving exponential equations with logarithms.
So the language and the logic of algebra can help us save lives, but it can be put to use to help us with the more mundane decisions that we make every day. Whether or not you continue to study mathematics, algebra is something that you can always use. Thanks for joining us.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.